Okay, so is my slide visible? Okay, so today I will discuss some part of material characterization. So I'll start with thermal analysis. X-ray diffraction, previously I have taught like 2-3 times I have discussed. So if you guys need, then I can discuss again. But first let's see this. Then I will discuss some concepts about SEM. Then we'll see. Okay, so we know the general form of Cp, that is A plus Bt plus C T to the minus 2 plus goes on. And what is dH? It is basically integral of Cp/Tt from one temperature to another temperature. And one more important, Cp of liquid is always greater than Cp of solid. Why? Because liquid has more open structure. Okay, so when we apply heat, the atoms in the liquid can vibrate more as compared to that of solid, because solid has a compact structure. So that's why they can absorb more energy. So Cp is basically specific heat. That means the amount of energy that is required to increase 1 degree of temperature. So this is why Cp of liquid is greater than Cp of solid. Always remember this point. And we can show this graphically. Okay, suppose this is our enthalpy and this is our temperature. So what will the curve look like if we have a melting occurring? So first it will go like this. This is the liquid portion. Then there will be a straight line, straight drop in enthalpy, and then solid. So remember the slope is basically dH by dt, that is Cp. So this slope is Cp and this is higher. In the liquid portion it is more steep as compared to that of solid. This is the solid part. And this is what we call the delta HF of latent heat of fusion, we call this. Latent heat of fusion. Okay, so clear till now? Okay. Now let's look at phase transition. Like first order, second order, what does that mean? So what is first order phase transition? In this, the first differential of free energy is discontinuous. So what does that mean? We'll take one equation. This is a more familiar equation. I'll take this example. So suppose we take first derivative del G by del P at constant temperature. What it will be? V, because at constant temperature this becomes 0. So del G by del P equal to V. What can be the second one? Delta G by delta T at constant pressure equal to minus S. Okay, so these two will be discontinuous at the what do we call transition temperature, like melting point or any other phase transformation. So that point we can say transition temperature. So these two will be discontinuous. Okay, so you can show it graphically. This is the transition temperature, and this is for solid, this is for liquid. So you can see here at this point so this is the final curve. So at this point G is continuous, but what is del G by del T? That is minus S, that is entropy. So if you calculate entropy at this point, that will be discontinuous. Similarly, if you see enthalpy, so entropy is basically Cp by T dt, enthalpy is Cp dt. So we can see, we can show enthalpy in the same format as I have shown here already. This curve, it is continuous in liquid state, solid, but here there is a discontinuity. There is a drop, sharp drop in enthalpy. So this is indication of first order transformation. Similarly, if we see Cp versus T for first order transition, how it will occur? So it will come like this at the melting point. Okay, suppose this is the melting point. At this point, this becomes infinite. Then it will go something like this. So here to here, there is no Cp, or it is infinite. Why? Because we know at melting, what happens? No matter how much heat we apply, the temperature doesn't change. until the whole material, whole solid becomes liquid. So this is why we call Cp is infinite at the melting point, because no matter how much heat we apply, the temperature won't change until we have all the solid is melted at the melting point. Okay, any doubt in this? Okay, so now we'll see second order phase transition. What is that? So in this, the second differential of free energy is discontinuous. So we can take one example. Like suppose we take the second differential of G with respect to T. So what is that? We know del G by del T minus S. We can take S. So first differential of G with respect to T is S. Second differential will be del S by del T, that is basically Cp by T. So in second order transition, what we see, the free energy will be continuous. Entropy, whatever was the first differential, they all will be continuous, including G. But the second differential, here it is Cp by T, or we can take just Cp. Discontinuous. You can see if we take G versus T, it will be something like this. So it will be continuous at the transformation temperature or critical temperature. This will be continuous. Similarly, H, as we had in the first order transition, here it will be different. Something like this. This will be also continuous. And Cp, it will vary like this. See here what happened. Here Cp is continuous, here continuous. At this point, at the melting point, Cp becomes infinite. in the first order transition, but in the second order transition it is something like this. It goes to some value, then suddenly it drops and it goes like this. So typically this happens. So what are the examples of second order? First order transition, we can say the way to differentiate first order from second order is we have sharp boundary. Like melting, we have a sharp boundary between liquid and solid, or some other solid state phase transformations. Where you can clearly separate two phases. And what is the example of second order transition? The most important is glass transition. Order disorder transition. Magnetic transition, like ferromagnetic to paramagnetic. In all these cases, second order transition, delta S equal to 0, no change in delta H, delta S equal to 0, delta Z equal to 0. Remember, only what is the change? Cp changes, that's all. So one question that was previous gate question, like in magnetic transition, what changes? Delta H, delta S, delta G, Cp. So remember, Cp changes only in case of second order transition. Now let's discuss some thermal analysis, like DTA, differential thermal analysis. In this, what we do, we have a reference material and we have a sample. So reference material could be nickel or some like alumina Al2O3. Sample, whatever we have, we can choose. So what we do, we heat the material, both heating rate normally ranges between 5 Kelvin per minute to 100 Kelvin per minute. Okay. So as temperature goes up, Cp will also go up. So then what we plot is this delta T versus temperature. Okay, so first as we heat the material, so remember this reference material should be such that melting point of this should be higher than the sample material. So when this melts, there should not be any phase transformation in the reference material. So as the temperature goes up, we'll see a plot like this where the delta T is maintained constant. And this is going up because there will be some Cp difference between the reference and the sample. So at the point where melting starts, so because till now the temperature difference is same for both the materials, so we are not seeing any peak. So as melting of the sample starts, what happens? That will start to absorb energy, because melting is an endothermic phenomena. So then the temperature difference of the sample and the reference will rise. Okay, then it will go down like this, then it will go, after the melting occurs, it will go like this. So this is the start of melting, and this peak, what it indicates, this indicates the highest rate of melting, highest rate of phase transformation. So just notice this, till now temperature is constant. As the melting starts, the temperature difference will, because one, for reference material the temperature is rising, but the sample material, as melting is occurring, so temperature will not rise. As I said, the Cp becomes infinite at the melting point, so the temperature of this will not rise, the temperature of reference will rise. So there will be a temperature difference, so we get this peak because of that. And after melting is completed, then the temperature of sample will also then start rising, so it will match up. Then another term is called differential scanning calorimetry, or DSC. So here what we do, here we maintain the temperature constant. And what we measure, temperature constant means temperature of reference and sample, and we measure delta H, that is change in enthalpy required to maintain the temperature constant. Okay, so remember this point, temperature we have to maintain the temperature constant, and we measure what is the enthalpy change required for both the materials to maintain the temperature same for both reference and sample. So in this the plot is the dH, or enthalpy, change in enthalpy of both reference and sample versus temperature. So in this we get a plot like this, the enthalpy goes on constant. Okay, sorry. So in this, when there is a transformation, start of transformation, we get a peak like this. So generally we consider this as endothermic peak, and upside it is exo. So if we start heating a material, so what will happen, this will be the melting point. Melting will start here. So because we know melting is an endothermic process. Why? Because to melt a material we have to apply the latent heat of fusion. That much we must apply to melt the material. Or when during solidification, we have to extract this delta HF, then only solidification will occur. Okay, so this is called exothermic process. Solidification and melting is called endothermic process, remember. So this type of peak we get when transformation starts, and this area under this peak, that will give the delta H or the enthalpy change for this reaction. Like this for melting or like this for solidification or crystallization. So this will give the enthalpy change values for that particular reaction. So DSC is more sensitive than differential thermal analysis DTA, and we can measure the enthalpy change of solid state reactions, which is very low, which we cannot measure in DTA, but in DSC we can easily measure the enthalpy change of solid state phase transformations. And one important for glass transition, I will show here the DSC curve for glass transition. So this will go like this, and then there will be a drop which just indicates change in Cp. So then it will go like this. This is the glass transition temperature Tz. After that point, this will be liquid state. Okay. Then there will be crystallization. You will get a peak. So this is the crystallization point. So in this region, it will be in liquid state. Again here. So this is called, like, solidification will occur here. Delta H of crystallization. Again that will go, and here it will melt. This is the melting point. Enthalpy of melting. Okay, so here this one indicates second order transition. There will be only Cp change, no enthalpy change. And again here the material will crystallize, and then it will melt here. Any questions here? Okay, so now I'll discuss some concepts about scattering electron microscopy. So first let us consider electron interactions, how that occurs. So we have three types of, one is primary electron, that is the beam electron. One is secondary electron, and one is backscattered electron. Suppose you have electrons like this, and this is our nucleus. So we have electron beam. Let's take one electron. Let's consider the primary electron, that is the beam electron, that hits this electron, and this is removed. So this removed electron, this will be called secondary electron. This is the primary electron. And the interaction between them, that is inelastic. Okay, so this is the nucleus inside. So we have a primary electron here from the beam. So it goes like this, and then due to the interaction with the nucleus, it comes out like this. This electron we call backscattered electron. And the interaction is, this interacts with the nucleus elastically. With nucleus and comes out with approximately same energy. Another important signal we get, that is characteristic X-rays. This is the nucleus, these are electrons. This is primary electron, that is beam electron. So suppose this knocks out this electron, so a vacancy is created here, and that is unstable. To stabilize this, an electron from a higher orbit will come to this place. So suppose this electron will come here. So in that process it has to lose some energy. So that energy will come out as characteristic X-rays. Okay, so this electron is removed by primary electron, and there is a vacancy. To fill that vacancy, a higher cell electron will come there, and to go there it has to emit certain energy, that is the energy difference between this cell and this cell. Call this KLM. So exactly the energy difference that will be emitted by this electron, so that will be come out as characteristic X-rays. So how electron beam interacts with the sample? Okay, this is the electron beam. Then it will form a teardrop shaped volume. This is the sample surface. It will form, the interaction volume will be something like this. So from the top surface, about 5 nanometers deep, so we call this OJ electron. These will be emitted. So what are these? Suppose here in this diagram I will explain this. Suppose this primary electron that knocked out this electron, okay, so this electron will go to fill the vacancy. So while going, it emitted this characteristic X-rays. Okay, so while this energy is moving, suppose this electron, this will absorb this energy and it will go out. So that one we call OJ electron. So it absorbs the energy emitted by this electron, and it gets enough energy to go out of the atom. So that kind of electrons we call OJ electron. So that will come from close to the surface. Then after that we have secondary electron. This will come about 5 nanometers depth OJ electron. Secondary electrons 5 to 50 nanometers depth. Then here we get, this is for backscatter electron. Backscatter electrons will be emitted from this region. And then after that we have so many like characteristic X-rays, fluorescence, all these things that will come from further deeper. So what is resolution? What the definition of resolution is? Smallest distance between 2 points that can be so there are 3-4 factors that govern this resolution. One is the applied voltage, one is current, probe current, one is working distance, so how voltage affects? So we can write interaction volume that is proportional to voltage. P for primary electron. Okay, so I forgot to discuss about the source. Like, okay, I'll see. So basically we use a thermionic emission, source, or field emission source to generate the electron beam. So in thermionic emission, what we do, we apply temperature, heat up the source, and that generates electrons. Generally we use tungsten filament here. In field emission source, what we use, we apply electric field. So with the application of electric field, the electron beam is generated. So here most frequently we use LaB6 filament, lanthanum hexaboride, LaB6 filament, that is used in field emission guns. So there is a source and we apply accelerating voltage here, and there is a system of electromagnetic lenses which control the beam, and here we have our sample. And there are some sources, like this is our sample detector. Our backscattered electron detector will be just above this, above the sample, and the secondary electron detector will be somewhere at the side like this, and the backscattered electron will be like a ring above the sample. So how voltage controls resolution is, if we apply low voltage, then the volume of the interaction volume will be smaller. So in that case, what will happen? Aberrations like spherical aberration or chromatic aberration so they will be more, so they will reduce the resolution. So for good resolution we should apply high voltage. So this spherical aberration is related to the electromagnetic lens, and this chromatic aberration is related to the energy spread of the beam. So high voltage required for good resolution, because if the voltage goes small, then these things will dominate and we will not get a good quality picture. So second is working distance. Suppose this is our electron beam and this is our sample surface. This is called working distance. So this has important relation to depth of field. Now what is depth of field? It is like if we move this sample from this place to further this side or this side, the focus will not change. Drastically. This is why SCM is used for fracture surface analysis. Because with the change in this distance, either up or down, the focus doesn't change much. This is called depth of field. And how it is related to working distance? So I'll draw this here. Suppose we have a large working distance like this. Okay, so see, in this case, if we move the sample slightly this way or this way, the focus will not change much, because the working distance or the depth of field depends on this semi angle. This angle, this we call alpha p. Okay, so smaller this angle, better the depth of field. So this is for large working distance. For small working distance, what we see like this. So this alpha p is bigger. That means if we change little bit the sample this way or this way, there will be large change in focus. So this is not good depth of field. This one, good depth of field. So to get good depth of field, you have to use large working distance or small alpha p. This is the point. Okay, so any questions here? Okay, so last Sunday I skipped one class because I was sick. So next Sunday, like I'm instructed to take 2 hours of class, like 7 to 9. So is that okay? Okay, so you can, like, next class I think I have phase transformations. So related to phase transformation, if you guys like have some doubt, previously you read something, if you have any doubt, you can directly ask me there. Like maybe it's some gate problem or some concept, anything. Like in 1 hour it is very difficult to cover all the concepts. So I'm just trying as much as I can. But still there are a lot of things that are left. So you guys should read it like on yourself and ask me if there is any doubt. Okay, so thank you. See you guys next week.